Well, everybody's here though, so that's good. So we have added 1. That's going to be 1/2 positive. Now we're going to divide by positive 1/2. Dividing by positive 1/2 is the same as multiplying by 2. Right? We saw that back here in this problem. Now we've got to add on our c. So what do we get for f prime? For f prime, we get 6t to the 1/2 plus c. Okay, plus c. Now, I don't know what c is. C represents, in this black version of the problem, C represents every constant. However, they have told us we want the one derivative that when you put 4 in for t, 7 comes out. That's the one we want. We don't want 6t to the 1/2 plus c, where that represents all possible answers in the family of solutions. We want the one answer that goes through the point 4, 7. That's the one we want. We only want one. We want that specific one. That's what this initial condition means. It means over here someplace, there's a derivative. We have it drawn right here, 6t to the 1/2 plus c. We want the one that goes through the point 4, 7. That's the one we want. That's what this says. I want the one that goes through 4, 7. I don't want all of them. I only want that one. That's the one that's important to my situation. So how am I going to find that? Well, I'm going to plug in 4 and make 7 show up. So I'm going to come over here and I'm going to say f prime of 4 is supposed to give me 7. What do I get when I put 4 in here? I get 6. I get 4 to the 1/2, and I get c. Well, I can solve this. You can solve this. We can all solve this. That's the square root of 4. So that's 6 times 2. That's 12 plus c is supposed to equal 7. Well, if 12 plus c is supposed to equal 7, we all know c has to be -5. And instead of having an infinite number of values for c, we now have one specific value of c. And now, at this point, and it's really important that we do it here and now, we rewrite our derivative. Instead of writing 6t to the 1/2 plus c, we write 6t to the 1/2 minus 5. But we're not done. We haven't answered the question. The question is, what's f? Not what's f prime. We have certainly found f prime. But now they want us to find f. They want us to find the function itself. So how do we do that? We anti-differentiate again. If I take the antiderivative of this, I'm going to get f. So I just duplicate my work. I keep my 6. I add 1, and I add 1. So that's going to be t to the 3/2 now, right? 1/2 plus 1, 3/2. I divide by 3/2. That's the same as multiplying by 2/3. Minus 5. It's not written here, but there's a t to the 0 right here. We don't write it. We never write it. We never wrote that in Algebra 1 once, but it's there, which means when I take the antiderivative, I add 1, and so I get t to the 1st. And then I have to remember to tack on my constant. Now, in a differential equations class, which all of you are going to get to someday, we're just going to call this thing c. It's not that c, it's this c. But I'm going to make it d tonight so we don't get confused. Now, what does this equal when we get all said and done here? 6 times 2 is 12. 12 divided by 3 is 4. So I have 4 t to the 3/2 minus 5t plus d. That's the function they asked me to find. Almost. Almost. Because there's a condition they put on my function. They told me I don't want all the functions with all the constants. I want the function that goes through 420. That's the one. I know, I see the numbers. That's the one they want me to find. So How am I going to find that version of this function? I'm going to plug in 4, and I'm going to make 20 come out. So I'm going to write here, I'm going to write f of 4 equals 20. And then I'm going to plug 4 in over here, just like I did here in red. I'm going to plug in 4. So this is going to be 4 times 4 to the 3/2 minus 5 times 4 plus d. And then we're going to solve this equation, just like we did before. We're going to solve this. Now, my suggestion, and I make this to every calculus class I teach, when you have a power like 3/2, take the square root. Take the square root first, because otherwise you got 4 to the 3rd. Now you're trying to take the square root of 4 to the 3rd. In this case, it doesn't turn out to be that bad, but in some problems, it turns out to be heinously ugly. So the square root of 4 is 2. 2 cubed is 8. 4 times 8 is 32. So this is going to be 32. This is minus 20, right? 5 times 4 plus d. So that equals 32 minus 20 is 12 plus d. Now that's supposed to equal 20. Because it's supposed to equal 20, that tells me that d equals 8. And at this point, we have finally come to the conclusion that they've asked us to find. We now know what f is. We now know what f of t is. We can write that right here. We can say, well, I found f of t. I know what f of t is. F of t is going to be this equation right here. But we're going to, in place of d, we're going to put 8. So it's going to be 4t to the 3/2 5t plus 8. And if we take the derivative of that twice, we should definitely get 3t to the minus 1/2. And we will. We will get 3t to the minus 1/2. So that's how we do a problem when they present us initial conditions. Right. Now, because most of you are majoring in something that requires physics, I'm going to just do something real quick here. It also has something to do with the homework. But I just want to show you something from your physics class, which if you're taking physics right now, is going to frustrate you. But if you're not taking physics and you haven't taken it yet, it's going to be enlightening and hopeful. And if you've already taken physics, you're going to wish somebody had showed you this a long time ago. Let's talk about 3 functions you know very well, especially if you've taken physics. We're going to talk about x of t, v of t, and a of t. X of t is position. V of t is velocity. And a of t is acceleration. Now, back when we were doing derivatives, we learned a relationship between these functions. I taught you when we were learning these functions, or when we were learning derivatives, that the derivative of position is velocity. In other words, I told you that if you take the derivative of position, you get velocity. I also told you that if you take the derivative of velocity, you get acceleration. Now, because of the relationship between the derivatives, that means if you take the second derivative of position, you also get acceleration. We talked about this back in chapter 3, and we had some homework problems where they asked about velocity and acceleration.
Hey, Kevin?
Yeah, go ahead.
Can you pull your board down just a little bit? I can't see that what you wrote on top.
I don't know what's going on. Sam, it's not me moving the board. It's the flip. I don't know how the camera moves. Now, this is going to get you guys really seasick, so I apologize.
Thank you.
Yeah, you're welcome. It's only going to wiggle for like 14, 15 minutes. It's a big old huge light bar that's hanging over the pool table, and I have the camera gorilla taped to a piece of it. And so I don't know why it moves. Maybe the house is falling down. I just don't know. I built it, so if it does, it's my fault, right? So let's just do this. And then, so here's where all of this is going. If you look in your book, there aren't many problems like what I'm about to talk about. But it's something that all of us, since we're engineering, scientifically oriented STEM people, we need to know this relationship. And more importantly, we need to know that not only does derivatives work going this way, antiderivatives work going this way. So I think a lot of us are aware that on the planet Earth, we have gravity, right? We have acceleration due to gravity. It holds us to the ground. It's a constant. It doesn't change. Technically, it does, right? You go to the top of the highest mountain, you go to the bottom of the lowest ocean, you get different readings for gravity. Not in a way that's going to affect too many things, to be perfectly frank with you, but they are different because you're further away from the center of the Earth or closer. But if we say acceleration equals a constant, we just call it a constant, and it's 9.8 meters per second squared, but we're just going to call it A. If I take the antiderivative of acceleration, I go this direction. Derivatives move down. Antiderivatives move back. If I take the antiderivative of this, I get velocity. Velocity is nothing more than the antiderivative of this. Now you and I, we know what the antiderivative of this is. There is, we don't write it, but there's a t to the 0 right here. We never wrote that in Algebra 1. I know I already said that once because that's what I say every time. And so when we take the antiderivative, we get a times t to the first plus some arbitrary constant. Well, a real amazing thing is going to happen here just in a second. If we say, let's assume that at time 0, our velocity is going to be called v naught. In physics, we like to use this. We call it v naught. We say initial velocity, right? That's what we say. So what does that mean? Well, that means when I plug in a 0, the initial velocity comes out. So if I come back over here and plug in a 0, I'm going to get a times 0 plus c, and that's supposed to equal v naught. Well, a times 0 is 0, so I get 0 plus c equals v naught. And that tells me who c is. C is my initial velocity. So if I bring this problem down here and rewrite it, I get this. Now, for all of you that are taking physics or have taken physics and you're studying kinematics, the motion part of physics, that's a formula you spend a lot of time trying to remember. You try to remember that velocity at time t is equal to acceleration at time t plus initial velocity. Now, a stranger thing happens if you take the antiderivative again. If you take the antiderivative of velocity, you're going to get acceleration. Sorry, position. And if you do that, what do you end up with? You end up with this crazy equation. This is a constant, so that's going to stay here. You add 1 to this power. This power is 1, so you get t squared. You divide by 2. That's how you take an antiderivative. Right here, you get v naught times t, because there's a t to the 0 sitting there, and you add another arbitrary constant. Normally, what they tell us in these kind of physics problems is that our position at time 0 is called x sub 0, our initial position. And if we plug this in, right, if we plug this in, we get x at 0 is equal to a times 0 squared over 2 plus v naught times 0 plus d, and that's supposed to equal initial position. Well, that's 0, that's 0, so d equals v naught, sorry, x naught. Which means we can rewrite this equation like this. This is x of t equals 1/2 AT squared plus V naught T plus X naught. And if you're taking, again, a Physics 1 class, you spend most of your first semester trying to remember this formula and this formula. And and if you took physics in high school, that's your whole first semester. I mean, you spent 15 weeks trying to learn those two formulas in high school, and I just got them for you in 7 minutes. So for all you calc kids, this for all you physics kids, you're all calc kids. This antiderivative thing, well, it kind of pays off. It explains where all the formulas for kinematics come from in Calc 1. So that's my gift to you for a Wednesday night when it's raining outside. Normally, in my high school classes, when I do that, they all ask if we can fire a physics teacher. I never understood where those. I never even that's all there is to that. Yeah, that's all there is. Physics isn't really that hard, guys.
Kevin, why do they make physics?
I say that not because I'm disrespecting you. That is not it. I say that because in high school, Kevin failed algebra 3 times. Twice. I apologize. Twice. I failed twice. I got a C the third time I passed. But when I took physics in high school, I was in algebra 2, so I didn't know any trigonometry. And I still got an A in physics without knowing trig. So physics can't be that hard. If I'm dummy me could get an A in there. And when we got to trig, I was asking everybody in class, what's sin and cos? And they're like, oh, dude, you're in trouble in this class. I'm like, I'll figure it out. So physics, it's just logic. Just think your way through it. You'll make it. When you take physics, just don't blame your physics teacher. It's not their fault. All of them suck. So 13C, Kylie, from 4.3. Is that, Kylie, I can't, is that one of those problems 45 minutes?
Well, I just wanted the C part, but I figured it out. So
You did?
Yeah.
Okay. Well, I respect you for that, young lady. Nice job. I respected you anyway, but I mean, damn, it's raining again. Sorry. I just keep thinking I should be building a boat. I've lived here for 57 years, and this is, we've had rain, but maybe the world isn't. All right. So what are we going to do now? We're going to talk about 5.1. All right. Now, how is this going to go? I think pretty well, especially if you've already watched the video, because it's going to seem pretty familiar to you. If you haven't watched the video, well, then, you're making this harder than it should be. Because I'm going to deliver this lecture assuming you've watched the video. Now, that doesn't mean that I'm not going to cover all of the information that they have in here. It just means that, there's a lot of information here, and it's going to go by pretty quick. I would strongly suggest, instead of using the recording of this, which is going to be 40 minutes long, I would strongly suggest you use the video from section 5.1, which is about an hour long. It'll have more detail and more examples in it. So here we go. Integrals. That's what chapter 5 is about, right? I mean, if we look at the title of chapter 5 says integrals, and 5.1 doesn't. 5.1 says area and distance. Now, that brings us a certain level of comfort, because, I mean, come on, if we're going to talk about area and distance, it can't be that bad. We're experts on area and distance. We know how to find area. We can find area of all kinds of magical shapes. Distance, we know how to find the distance. We have the distance formula. We've seen the distance formula. Heck, in pre-calc, we saw the distance formula in 3 space. Man, we can find the distance anywhere. But because we're in chapter 5 of calculus book, there's probably something about that word area and that word distance over there that we haven't really considered yet. Because as good as we are at finding area and distance, and we are solid at finding area and distance, we're only as good as the techniques we've been presented. And unfortunately for us, we have not been presented all the techniques. We've been presented, the Euclidean geometry approach to area and the Euclidean geometric approach to distance. What we've not been asked to find or consider or even think about are things like something as simple as this. And if you're thinking, well, that's the same example he used in the video, well, you're right, because it's the same example Newton used when he taught calculus first time. And who am I to go off the freaking script when it was good enough for Newton? It's good enough for Kevin. You and I can't find the area of something as simple as that shape right there, right? We're stuck. We're incapable of finding the area of this. We can clearly see it's not a triangle. We know it's not a rectangle. And the other thing that holds us back is that arc right there is not the edge of the circle. We could do this, right? We could do this if that was the edge of the circle. We're magical when it comes to triangles and circles. Those are the two things we can satisfactorily find the area of. And don't think that, you know, that I'm exaggerating, because if you draw a polygon, you can always make this polygon into triangles. And if it happens to have a circle attached to it, that's even easier. But I can't draw a polygon you can't make into a collection of triangles. There's a theorem in geometry that says that. So every polygon can be broken down to a set of triangles. And because it can be broken down to a set of triangles, we all know about half base times height. We can all find the area of any polygon. What we can't find the area about is something as simple as this. So how are we going to attack this problem? What are we going to do? How are we going to attempt to find the area of something that's relatively not complicated? Not complicated in the calculus context, very complicated in the 3rd grade, 4th grade, 7th grade approach to area and distance. But for us, come on, it's just a quadratic, right? It's a parabola. It can't be that hard to find the area of this thing. So what are we going to do? How are we going to overcome that? Well, we're going to use a technique that is, well, it's as old as Euclidean geometry, to be honest with you, because the Greeks knew how to find the area of that. And I say that with the caveat. They knew how to find the area of that. They didn't know how to do it. They knew what to do. They just didn't have the math to get it done. It wasn't until we got the concept of a limit that you and I became capable of finding the area of this. And of course, it's going to be a limit because we're in a calculus book and everything in a calculus book is limits. So how do we go about, I'm going to redraw that now. How do we go about finding the area of something like this? You know, we've got our parabola. This is the point 1, 1. How do we find the area of this? Well, we go with our strengths, right? I mean, that's what I do. Whenever I find myself in an uncertain situation, I just go back to my, my strengths. You that self-deprecating humor, to be honest with you, and you're all shaking your head because you know that's true. So how are we going to find the area of this? Well, we're going to go to our strengths, and our strengths are polygons. And in this case, we're not going to go very far. We're not even going to touch the triangle. We're going to go straight to the rectangle. Okay? What are we going to do? We're going to look at this and we're going to say, well, this is 0. This is 1. We're going to call this the right-hand side. We're going to call this the left-hand side. And we're going to say to ourselves, if I draw a rectangle using the right-hand endpoint as my height, that's an estimate of the area. And we know that rectangle is 1 wide by 1 high. We have notation for that. Our notation is R1. Okay, R1, that's our notation. R means right, not wrong, right. And 1 means we only drew 1 rectangle. And if we find the area of that rectangle right there, it's 1 by 1, we would write that as 1 times 1, and we would get 1. And we know we're wrong. But that's okay, we're estimating. Now, there's another approach, right? We have the right-hand approach, which we did right there in red. We can do the left-hand approach. The left-hand approach, just take the left-hand side, draw a rectangle that's that high. We're going to call that, yep, you guessed it, L1. That rectangle is 1 wide by 0 high, and it gets us an answer of 0. And we know that's wrong, right? That's wrong. It's too small. 1 is too big, 0 is too small. So our approach is to just go with our strengths. Use calculus. Let's let the number of rectangles grow. Instead of doing 1 rectangle, let's do 2 rectangles. And if we're going to do two rectangles, be nice if that was in the middle, huh? Okay. I wasn't the only one that was bothering, so don't act like I was. If we do two rectangles and we use the right-hand approach again, the right-hand approach, now this one's going to start here on the right-hand side, right? I'm on the right-hand side of this interval. I'm going to start up here on the right-hand side, but I'm only going to go this far because I come to my next endpoint. And then I start on the right-hand side and I go across here.
Why the screen?
And that was the pin. And now my answer is a lot better than it was before, right? We're a lot closer to the real answer. We don't have the right answer. That's way too much. It's too big. We can all see this is too much and this is too much, but we can write down what R2 gives us. R sub 2 is going to be, the width of this is going to be a half now, right? Not 1 anymore. It's going to be a half. And we're going to multiply it by the height. Now, don't forget, our function here is y equals x squared. So x is a half. So I get a half squared as my height. Over here, my width is a half, right? Still a rectangle. My width is a half, so that's going to be a half. My height on the right-hand side is 1. So I'm going to multiply that by 1 squared. And what do we get? We get an 8 plus a half, right? So we get a half plus a half squared is a 4. So a half times a 4, that's going to be an 8. Here we get a half. I'm going to write a half as 4/8, and we get 5/8, which we know is wrong. Everybody on here knows it's wrong. We know it's wrong. The plants around me know it's wrong. That's wrong. But it's better than R1. It's better. It's more accurate. Now, I'm going to stop looking after this. I'll do L2 right here, but then I'm going to stop worrying about L's because otherwise we're going to get weeded down on what's the left, what's the right, we're just going to talk about it from the right-hand side. So what does it look like if we draw from the left-hand side? Again, put your fingers down. It helps. This one's on the left, right? This is the left. So that's going to be this high because that's my left-hand endpoint. Then I go over here. This one's on the left. So I go to that, and it's going to be this high. Now, that's going to be wrong. We know that's going to be wrong because we don't have any of this, and we left out all of that. But it's going to be closer to what we had before. What we had before was 0. Right? What we had before was 0. Now, what do we have? We have a width of a half here. We have a height of 0. I'm going to square that. And then over here, we have a width of a half. And we have a height of a half squared. Right? Because that's our left-hand endpoint. So that's what we plug in. And we get 1/8. And we know that's wrong. But we know the answer is somewhere between 5/8 and 1/8. Right? Somewhere in between. 1/8 is a lower bound. 5/8 is an upper bound. Now, as I let the number of rectangles grow, my answer is going to get better and better and better. And that's what your homework in section 5.1 looks like. Your homework in section 5.1 looks like this. Exactly what I'm doing right here. That's what you're going to do in section 5.1. They're going to tell you how many rectangles, and you're going to partition, that's the word we use. You're going to partition this interval into that many rectangles. You're going to use either the right-hand side or the left-hand side, depending on which they tell you to use in the problem. And you are literally going to find the area of a whole bunch of rectangles. And you are going to do this knowing in the back of your mind that the more rectangles you use, the more accurate this is going to be. Because I'll use my blue pen here. If we make this 4 rectangles, if we make this 4 rectangles, it would look like this. And if we do the right-hand side, remember I'm starting on the right. If we look at the right-hand analysis, R sub 4, we can see we're way better off than we were with R sub 2. I mean, with R sub 2, we had all of this up here, which we didn't want, and now we've eliminated it. With R sub 2, we had all of this over here, which we didn't want, and now we've eliminated that. So R sub 4 is going to be better than R sub 2. R sub 8 is going to be better than R sub 4. R sub 16 is going to be better than R sub 8. R sub 32, and on and on and on this process is going to go. Now, the good news is in the homework, they're not going to ask you to find R sub 16. They're not going to ask you to find R sub 32. Right? They're going to ask you to find like R sub 6, R sub 8. And to do that, right, I'll give you some hints right now to help you with the homework. They're on the video as well. This is 1/4, of course. This is 3/4. My first hint on the video is common denominators are really important when you do this problem. Really important. Okay? Common denominators are really helpful. So no matter what your denominator is, you want to make them all the same. Okay? All the same. Now, what is this going to look like? Well, we'll start here. 2 fingers. Again, it's a big deal. It helps. This is on the right-hand side. Okay. How wide is this? It's 1/4 wide. How tall is it? It's this person, right? Because we're on the graph. It's this person, so that's 1/4 squared. What about here? This is on the right. It's 1/4 wide. Don't forget the width. And it's 2/4 squared. This one's on the right. 1/4 wide. 3/4 squared. This is literally your homework. This is what you're going to do. 1/4 wide. 4/4 squared. Okay. Trust me, these common denominators are really going to help. Because look, we can factor now. There's a 4 squared, there's a 4 squared, there's a 4 squared, there's a 4 squared. There's 4 to the first, 4 to the first, 4 to the first, 4 to the first. That's 4 cubed. The top is 1 times 1 squared, 1 times 2 squared, 1 times 3 squared, 1 times 4 squared. All right. Now, it doesn't take a rocket scientist to add this up. That's 16 and that's 4. So that's 20. That's 9. That's 1. That's 30. And 4 cubed is 64, and we get 15/32. Which is not right. It's not right. It's blatantly wrong. We can all see how it's wrong. We all see it's way too big. We have this piece we didn't want. We have this piece we didn't want. We have this piece we didn't want. And we have this piece we didn't want. But the purpose of section 5.1 is for us to understand beyond a shadow of a doubt that the more rectangles we draw, the more accurate this picture is going to become. That's where we have to exit 5.1 as a student. When we leave 5.1, we have to know what was the purpose of drawing all these rectangles. Why did they have me do this? And the reason they had us do this is because we have to know as the number of rectangles grows without bound, the error goes to 0. Because every time, and don't do this on your paper because it's going to become arduous and ridiculous, but I'll split this one more time with black. And I'll draw the rectangles again, and it's going to become a mess, I know. But if you look, we're better than we were before, right? Now, if you allow me to just grab this rag and start doing some erasing, we got rid of all of that error, right? We got rid of this error right here. We got rid of this error right here, and we got rid of this error right here. So now our mistakes, while they're still there, while we still have error, right? We're too big there, and we're too big there, and we're too big, and we're too big, and we're too big. We're not nearly as bad off as we were when we only had 2 rectangles. Just to remind you what 2 rectangles look like. 2 rectangles look like this. Right? This is what 2 rectangles. Look at all the error we got rid of. So we're going to find the error by letting the number of rectangles grow. The Greeks had a name for this. Again, they didn't really understand how to do the math. They knew the process. They called this the method of exhaustion. And that is an aptly chosen name for this. We're going to do this until we're exhausted. We're going to just keep doing it over and over and over and over and over. We're going to let the number of rectangles grow without bound. 4 was good, 8 is better. 8 was good, 16 is better. 16 was good, 32 is better. 32 was good, do 64. And every time we let the number increase, the errors decrease. Right? The errors. And of course, you don't have to do it from the right-hand side. You can do it from the left-hand side. It doesn't matter. It doesn't matter. Okay. Now, where does all of this go? Well, believe it or not, it goes to exactly where I keep telling you it's going to go. It goes to the point that we do this not with 1 rectangle, not with 2 rectangles, not even with 4 or 6 or 8 rectangles. To show you how smart you are, we're going to do this right now because you're ready. You're only in section 5.1. I understand, but you're ready to do this with n rectangles because you're a calc student in chapter freaking 5. You're good. You got this. It's going to look burdensome, involved, but it's not hard. Every single time we do this, it's going to be width times height, width times height, width times height, width times height. And if you can keep track of what you're doing, then you're going to be fine. So let's take and do what Newton did, right? I mean, it was good enough for Newton, it's good enough for us. And let's just take the function y equals x squared. And let's find the area under the curve from x equals 0 to x equals 1. Okay, that's what we're going to do. So we're going to draw the picture over here. Just get it out of the way. We'll draw the picture. We'll draw it really big. All right, we'll draw it over here. Draw our function. So we just got our parabola, right? We just got our friend the parabola. It goes like this. This is 1. This is 0. This is y equals x squared. And we're going to find that area. And we're going to find it. We're going to find not 15 over 32. That's a terrible approximation. We're going to find the real area. And how are we going to do that? We're going to do exactly what you and I, well, I'm doing all the talking, you're doing all the listening. We're going to do exactly what I said we're going to do. We're going to come over here and we're going to split this up. Okay? Not into 4 rectangles, not into 6 rectangles, not into 8 rectangles. We're going to split this up. So that's x sub 1, x sub 2, x sub 3. And I'm just going to keep going. And I'm going to call this person right here x sub n. All right? I'm going to make it into n rectangles. There are going to be n of these things. N of them. And we're going to use right-hand endpoints. So we're going to have n rectangles that look just like this. Okay? N of them. And those errors are going to be 0. When we get all done, when we're said and done with this, those errors are going to turn out to be 0. And it's not even hard math. It's just repeated addition with us paying attention to our widths and our heights. That's all that's going to happen here. And it's not going to overpower you. There's going to be a lot of symbols written here before we get done. Okay, a lot. But it's not anything that's complicated. It's involved, but that doesn't mean it's hard. So where are we going to go? We're going to go width times height, width times height, width times height, width times height, width times height. That's what we're going to do. We're going to add them all up. So the first thing we have to ask ourselves is, what's the width? Right? What's the width? What is that going to be? Well, the width, I've partitioned this into n parts. N. There's n of these rectangles. That's what the dot, dot, dot means. There's n of them. So how wide is it? Well, the width of each rectangle, I changed colors because I noticed the brown was hard to read. The width of each rectangle is going to equal what? What's it going to equal? Well, it's going to equal 1 minus 0 divided by n. Now, if you think that through for a second, that makes complete sense. If I was going to split this into 4 pieces, you would divide the length of this in 4. You're divided by 4. If I was, and it would be 1/4, 2/4, 3/4. You have that written in your notes. If I was going to make it into 8s, it'd be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. I divide by 8. Since I'm going to make it into n, I'm going to divide by n. That's what I'm going to do. So it's going to be 1/n. That's going to be the width of every one of these rectangles. So if I'm going to find r sub n, I just have to, it's going to be just like r sub 4. I just have to write it down carefully and everything's going to work out. It's going to work out just like r sub 4. As long as I write it carefully, it's all going to be okay. So I ask myself, okay, I'm going to do the same thing we did before. I'm putting 2 fingers down just like I did before. This one's on the right-hand side. All right, so I got to figure who this is. I got to figure who that is. Well, you know who that is, and I do not mean x sub 1. You're at 0, and how far to the right did we move? We moved 1/n. If you start at 0 and you move to the right 1/n, you're at 1/n. Isn't that true? I mean, if we were going a 4th and we started here, we'd be at a 4th. If we were going an 8th, we'd be at an 8th. We're at 1/n. Who is this person right here going to be? I'm going to put an arrow down here so I can fit it. Who is this person going to be? Well, I went 1/n, and then I went 1/n again. 1/n plus 1/n is 2 1/n's. Who is this person going to be? Well, I went 1/n plus 1/n plus 1/n. That's going to be 3/n. Now, if I think that I'm doing this correctly, I can check by moving down here. X sub 1 was 1/n. I'm looking for a pattern, just so you understand. X sub 2 was 2/n. X sub 3 was 3/n. X sub n, by that pattern, by this black pattern down here, X sub n is supposed to be n/n. What does n/n simplify to? Exactly what it's supposed to. So I'm doing it right. See, it's got a built-in check over here. And on the video, I make a big deal out of this built-in check. So we're going to do height times width, height times width, height times width, height times width, and we're going to write it down smartly. So let's do our first rectangle. Our first rectangle is 1/n wide. Here it is. This is the right-hand side. This is the right-hand side. How tall is it going to be? Well, it's going to be 1/n squared, because that's what our function does. It squares it. So it's going to be that times 1/n squared. What about the next one? Well, these are the 2 points right here, right? This is one on the right-hand side. How wide is it? Well, it goes from 1/n to 2/n. So it's 1/n wide again. They're all going to be the same width. So I get 1/n here. My height is going to be 2/n squared. I come back, I put my fingers down again. I point at the right-hand side. That's 3/n. I ask myself, how wide is this? It's 1/n. So I get 1/n times 3/n squared. Now, I'm not going to write them all down. I'm looking for a pattern. I go to the end. How wide is this last rectangle? 1/n. How tall is the last rectangle? n/n squared. Remember, I told you on the previous example, common denominators are key. Now, if you take a look at this, all of you can add that up. All of you can add that up. You don't think you can, but you can. I know you can. You don't know you can. You can all add this up. Everybody in the room knows there's a 1/n in every one of those terms. I keep saying everybody in the room because, I've been teaching for 35 years. We're not all in the same room. First time that's happened. There's a 1/n, there's a 1/n, there's a 1/n, there's a 1/n. Here's an n squared. See? N squared. N squared. N squared. N squared. The bottom is n cubed. Okay. What's on the top? 1 squared. 2 squared. 3 squared. We didn't write it down, but the next one's 4 squared. And this one just keeps going and going until we get to the last one, which is n squared. Now, some of you are sitting here looking at this thinking to yourselves, okay, I don't know how to add that up. That's not true. You do know how to add this up. You just forgot. Because in pre-calc, there was a day, and it happened when you were learning the binomial theorem, which also you forgot. There's a day where somebody taught you how to add up all the squares. They told you if you wanted to add up I squared, I equals 1 to n, which is what we're doing right here, that's n times n plus 1 times 2n plus 1 all over 6. Somebody taught you that. It happened in pre-calc. And if it didn't, I just taught it to you right now. So now you can, go to a bar and play with drunk people and see who wants to add up squares fastest and, take all their money. I used to do this in college all the time. My friends would wake up in the morning and be like, dude, I swear to God, I had 40 bucks last night. I'm like, man, last night you made a lot of stupid bets in a bar. You made a lot of dumb bets. Really? What did I do? You kept betting people you could add faster than everybody else. You lost all of your money, man. I watched you. Oh, dude, next time, save it. All right, I'll do that next time. Hey, didn't ask me if I took your money. I didn't lie to you. Everything I just told you was true. You were the idiot that kept betting me that you could add faster than I could. So what does this add up to, right? 1 squared plus 2 squared plus 3 squared plus 4 squared plus n squared. We know what that adds up to. It adds up to this. So what is this? This is n times n plus 1 times 2n plus 1, all divided by 6, right? That's the top. And now don't lose that. I have 1 over n cubed. Now, there is no purpose to multiply this out. None, absolutely none. All we have to do is do the first term. That top is 2n cubed plus some stuff. And I'm just going to call it stuff. The bottom is 6n cubed. Now that's it on the bottom. Now there's other terms on the top. There's other terms, but we don't need them. We don't care about them. They're not significant to us because we want this. This is what we want. We don't want to find r sub n. We want to know what happens when n goes to infinity for r sub n. We don't want to do this for n rectangles. The Greeks didn't say to do it for n rectangles. Newton didn't say to do it for n rectangles. Newton said to do it for all the rectangles. The Greeks said, exhaust yourself. Do it. Well, that means we want to take the limit of this. Well, that's a limit that on our chapter 1, 2 quiz, everybody in the room could get right. This is 2n cubed plus some garbage. This is 6n cubed. And we have a rule that says if the degree of the numerator is the same as the degree of the denominator, and you take a limit as n goes to infinity, you get the ratio of the leading coefficients. The area under there is 1/3. 1/3. And all we had to do to be able to find that area was do width times height and not get confused. And remember that formula right there. Which I admit none of us remember, but that's okay. That's why I'm here. Got to earn my money somewhere. The area under there is 1/3. It's exactly 1/3, by the way. It's not an ugly number. It's exactly 1/3. Now, because I like to, enlighten you, let's take a look at our function. All right, here we go. Here's the big moment, right? We got to close with the crescendo. You can't close with a whimper. What's the antiderivative of this? The antiderivative of this, right? The antiderivative of this is we add 1 and we divide by the new exponent. Right? That's the antiderivative, right? You add 1 to this, that's 3. You divide by 3. Now, a funny thing happens. I'm going to write 0 down here. And I'm going to write 1 up here because that was my left-hand endpoint and that was my right-hand endpoint. And then I'm going to plug them in. I'm going to plug 1 in to this, right? The antiderivative. I'm going to plug in 1. 1 cubed over 3 is 1/3. Now I'm going to plug in 0. 0 cubed over 3 is 0. And you know what we get? Same thing. That's what antiderivatives do for you right there. Antiderivatives find the area of the curves. That's what antiderivatives do. Now, we don't know that yet because all this stuff I wrote in red is in section 5.3 and I'm not supposed to show that to you yet. But I do want you to know that this is not what we're going to do for the rest of the semester. It's just what we're going to do for 2 sections. Okay? We're going to do it for 2. So we are going to do it. Why are we going to do it? Because if all I taught you is this red stuff, we wouldn't know what we were doing. We would just be moving symbols around. You'd be like, oh, you write this down, I take the antiderivative of this, I plug in that side, I plug in that side, a number comes out, I'm done. Yeah, what did you just do? Okay, let me show you again. You gave me this, I found the antiderivative, I plugged in that number, I plugged in that number, I subtracted, I got a number, I'm done. Okay, what'd you do? Dude, I think you're drunk. I'm not gonna take it a third time. Yeah, I know. It's because you can't tell me what you did. You don't know what you did. You have no connection between how this connects to this person right here. And everything in calculus connects to that. Right? Integrals are limits. Derivatives were limits. Everything in calculus is a limit. So we have to start with the understanding of where this red stuff comes from. And that's what 5.1 and 5.2 are about. Okay. So that's going to close out what we're doing tonight. I'll put my ugly mug back on here. You guys have, yeah, you have extra quiz time. Look at that. Well, actually, I guess you don't really have extra quiz time because the quiz hasn't landed on your laps yet. But we're gonna call it a night because I don't have anything else to talk about. So that was 5.1. You're now capable of doing your homework. All right. 24 of us, man. That's the most we've ever had for one of these meetings. So I would strongly suggest that you watch the video on 5.1. Yes, that what we just did right there is on the video in 5.1. So you don't even have to, watch the recorded class on Zoom. You could watch the video. It's a lot better. You don't have to watch me. And then I have the video on 5.2, and I will take care of some of the homework problems. It all comes down to organization. I mean, it all comes down to organization. If you can organize the way I organized on the board right there, and the way I organize in the videos, you're going to be fine. You're going to be fine. But you have to be organized. You don't know where Calc 2 is going. I know where Calc 2 is going. All you know about Calc 2 is, you're going off and cheating on me with somebody else. But organization is going to be the important thing. If you're not organized, if you can't write things down like that and keep all your thoughts going in a logical manner, Calc 2 is going to get kind of tough. I mean, even, not that it's easy. Calc 2 is the worst, just to be honest with you. That's why I don't want to teach it to you. I didn't choose not to teach it to you. But Calc 3 is great. When you get to Calc 3, you're going to love Calc 3. Oh, God, Calc 3 is so much fun. Calc 2 is the worst class. It's dry. Oh, it's so dry. Don't blame your teacher. It's not your teacher's fault. The material's dry. Okay, it's not the teacher's fault. I don't care who teaches it. Calc 2 is dry. All right, so you're off. You're ready to do the homework in 5.1. The video is out there. The video on 5.2 is already out there if you want to watch that. It also talks about problems exactly like this, very similar to this. So you're not going to see a lot of difference between 5.1 and 5.2. What is an integral? Why do I integrate? What does an integral do? It finds areas under the curve. That's what we know right now. There's going to be other things it'll do for us that we'll also discover down the road. But right now it finds the area under the curves. All right, so good luck on your quiz tonight. Email it to me. We said what? 8:32? Said something like that by 8:32. Something. Maybe it was maybe it was 10 o'clock. So take your time. Yes, Rag.
If you don't mind, can you write your email in the chat room?
Yeah, if I can type correctly, I can write my email in the chat room. Hold on. Let's see if I can do this.
So we're emailing it to you?
Email it to me as a PDF.
Okay.
Not as a photo from your phone, Jake. I don't want that.
Dang it.
I know.
Together.
I just got a scanner app on my phone. It's pretty cool because I had to do it earlier. So I just took a picture with the scanner app.
Oh
and it
yeah,
automatically
yeah.
scanned it for me.
It's a free app on your phone. You just
Yeah.
scan it with your phone. I mean, you just take a picture and it shoots it right to a PDF and you send it right back to me.
Mhm.
Hey, you can Jake, you have your iPad. You can download it to your Notability and just do it on there, and then email it to him from that.
These
That's
are
already
big
PDF,
words.
huh?
These are all big words, Adam. Notability. Is that even a word? I mean,
It's an app.
Notability is an app.
It's an
Yeah,
app
that's our note-taking app we use.
that I use on my iPad for taking notes. I actually record your lectures while I'm doing
I
this.
saw you in class there jamming away on an iPad. I just figured you were, playing a casino game. And
I'm trying
All
to make that money.
all right, guys. So everybody's good. We're all great. The rain's going to stop. Tomorrow I'm getting a puppy. So
What?
yeah, but we don't even have class Monday, right? We're on spring break now, right? Again, I don't know why we call this spring break. I'm probably gonna have a couple of office hours over spring break. If anyone's interested, I'll send those out over reminder. I'll give you a couple of days notice though. I won't do it like I did the class tonight. I didn't send that out until I will post a picture of the puppy. I'll get that out there. I have no idea which puppy I'm picking. We gotta go conduct a puppy test tomorrow. Find out which of the four is the smart one. So if you guys have any questions on the quiz, that's not my problem. It's not my problem. I'm not saying that you're going to call anyone. I'm hoping you're not. But you got a book, you got a notes. Heck, you can rewatch a video.
Adam doesn't answer anyway.
Well, Adam's an honest man. Everybody in class.
That's right.
How will we know our answer?
Oh, whether you got them right or not, Rag?
Yeah.
I will post a PDF of the solutions to the quiz at when's the quiz due? 10 o'clock?
Yeah.
Yeah.
Okay, I'll put the solutions up around 9:15, something like that.
Deal.
Tomorrow night, 9:15 tomorrow night, ladies and gentlemen, not
That's
tonight.
no fun.
Tomorrow.
Throw dog.
That's no fun.
So, all right, everybody have a great evening. It was great to interact with those of you that decide to turn your microphones on. Again, I say this every time, but I really
So for the midterm, are we gonna get a study guide?
a study guide, Sam.
No, a whole week off.
Sam, here's your study guide right here. Look, I got one right here for you. You got one of these? It's really cool. It's organized way better than any study guide I would make for you. It's got drawings and pictures, and that's what you're gonna get, Sam. You're gonna get a book. I'm sorry, dear, but that's it. That's all I can say. All right. Hey, but you don't have to worry about your note card anymore. It's open book, open notes. No note card. So although the note card may be more efficient than open book and open notes, but
Well, I had started my note card, and I'm like,
yeah, well, just use that and keep your book as a backup note card. All right, you guys have a good time with the quiz. I'm sure it's going to go fine. I wrote it hoping it was going to go fine. I wrote it I don't want to say so it was going to go fine, but I wrote it hoping it was going to go fine. He says, hopefully.
Rag said, what is covering in the midterm?
Oh, we'll talk. The midterm goes all the way through. Tonight was 5-1, right? And tonight's Wednesday.
Yes.
So this is where the midterm stops. The midterm stops here. 5-2, we're going to talk about 5-2 on Monday night before the midterm. I'm not going to put that on the midterm. So 5-2, 5-3, 5-4, 5-5, those are going to be on the final, but they are not on the second midterm. Okay.
Wait, what?
Well, we stop, Sam. We stop at 5.5. That's when we
Okay.
stop. So the midterm's going to stop though at 5.1, right?
Okay.
So we will
For our
never
second midterm.
take a midterm on 5.2, 5.3, 5.4, or 5.5. They'll just be on our final exam. That'll be the first time we're tested over those, is what I was saying. Does that make sense now?
Yes. I'm just making sure that I write it correctly
Mhm.
because I'm going to go back and be like, okay.
But this is all recorded, Sam. You just got to fast forward to this spot. True?
Is it? Oh, right.
Yeah. It'll be up on the YouTube channel in a few minutes. Well, actually, it takes about an hour for this thing to compress.
Yeah.
It'll be up there in a while. All right.
The last question of the evening.
Yes, Rag.
According to your chat, there is no 5.2, but are we covering 5.2?
Yeah, we're covering 5.2. I've already put the lesson for 5.2, the lecture for 5.2 up on YouTube.
Yeah, because in your schedule, we cannot see 5.2.
Oh, yeah, we cover 5.2. 5.2 and 5.1 are essentially the same thing.
Okay.
Yeah,
Maybe
we'll
it's
be
a
covering-
mistake.
but the midterm stops with tonight's lesson. This is where the midterm stops. It'll go no further than this. That last problem we did will be the last thing that you have to worry about for the midterm. Okay. And like I said, I'll have a couple of office hours during spring break. All right. So everybody have a good weekend, and I'll see you when I see you next week. I'll put that out on my mind. All right.
All right, I better start driving to CSUV now.
Can you get in there? Can you still?
Wait, is the library still open?
I don't know,
I
Sam.
thought it
Library-
was still open.
I don't
No?
know.
I don't think so. It's not open.
Okay, then I don't have a printer.
Sam.
Where do you live?
Sam, here's what you're going to do. You're going to take the quiz on your phone, and you're going to write it on binder paper, and then you're going to take a picture of it and download the app that'll turn that into a PDF and send it back to me.
Oh,
Okay.
nice idea.
Because I'm buying a printer, but some of the stores, they're closing early. So I'm
Yeah,
like,
it close a lot. Best Buy, you have to buy it online, and then they just walk it out to your car.
yeah.
So
So because I was gonna buy off of Best Buy, and then I was all like, wait, what's
yeah, you
this?
can't get in there. You can't get in. All right. So that's what you're going to do, Sam. You'll have to give me a handwritten copy back, but then on the midterm, it'll be all okay by then.
Yeah, I'm buying a printer
Perfect.
right. Well, after I do the quiz.
Yeah, don't do it. Don't do it before the quiz, Sam. It's not important. Tomorrow. You got all day tomorrow. All right. All right, everybody. I'm going to close out the meeting. I'll get this up on the YouTube channel as soon as I can. Everybody have a great night, and thanks for being here. See you guys later.